quantum physics is pretty weird, right? Things like the position of a particle isn't a set value, and when you measure it, the outcome is random. That's not how things act normally. So, how come quantum physics is so weird? Let's start with an easier question. If quantum physics is random, does that make it completely unpredictable? Not quite. As an analogy, let's talk about dice. Say I throw a die. What can I say about the outcome? Well, not much, right? It's random, much like quantum physics. It can land on any number from 1 to 6. But, say we throw 3 dice that land on, say, 1, 5, and 6. We can now talk about something you might already be familiar with, the average. The average of the 3 dice rolls is calculated by summing the value of each die and dividing by the number of dice. In this case, the average is 4. One way to conceptualize the average is as the answer to the question, how much would each die show if the total of the dice was evenly distributed among the 3 dice? Each outcome of the die throws has a 1 out of 6 chance. Let's also be clear on what that means. That means that if we throw a die many times, we expect roughly 1/6 of those throws to be 1, 1/6 of those will land on 2, and so on. So, say we throw many dice, say 300 dice. Is there anything we can say about the average before we know the results? Well, of course, we cannot say definitively what the average will be. It could be anywhere from 1 to 6. However, we can keep in mind that we expect each value to occur roughly 1/6 of the time each. With this in mind, our best guess for the throws is then to get exactly 50 of each of the 6 outcomes. This would give an average of 3.5. Now, I of course want to test this, but 300 dice I feel is a bit too many to do by hand. So to test this, I simulated 300 dice throws with the computer, the results of which you can see now. When all is said and done, I got an average of 3.537. This is pretty close to the value we predicted of 3.5. The theoretical value of 3.5 that we calculated is called the expectation value of a die roll. The expectation value, denoted by these angle brackets, can be thought of as the theoretical average of some random event, and is calculated by multiplying the value of each outcome by the probability of that outcome, and then summing all of that together. The fact that the average is fairly close to the expectation value when throwing a large number of dice is called the law of large numbers, which roughly states that for a given random event, the more times the event occurs, the closer the average of the events will be to the expectation value. So with that, let's get back to the physics. Say we have a particle in a force field, for example an electron in an electric field. When we say force field, what we mean is that each point in space is associated with some force. If the particle finds itself at a given point, it will be subject to the associated force. So, how will the particle move through this force field? Classically, that is to say, not quantum physically, the motion of the particle is described by Newton's second law. Newton's second law says that at a given instant in time, the momentum of the particle changes according to the force exerted on the particle at this instant. In this animation, the particle is subject to a rightwards force, which causes the momentum of the particle to be more and more rightwards. Quantum physically, however, both the position and the momentum of a particle is random. So what can we say about the motion of the particle? This is where Ehrenfest's theorem comes in. Ehrenfest's theorem states that while any individual measurement of position or momentum is random, the expectation value of the position and momentum follow Newton's second law. That is to say, any individual particle may behave unpredictably, but if you run an experiment many times, then the average of the paths that the particles will take closely follow Newton's second law. Now, that's pretty interesting in its own right, but it also kind of explains why quantum physics doesn't seem to match our intuition. Since we're made up of so many atoms and all of these atoms interact with each other so many times per second, we can apply the law of large numbers. That is to say, on a macroscopic scale, we will only really experience the averages of the individual particle interactions. Since these interactions are so many, the average will nigh on exactly be the expectation value. This is why, even though quantum physics is random, the universe seems to follow deterministic laws such as Newton's second law on macroscopic scales. So when we ask why quantum physics is so weird, it's really because in our day-to-day lives, we only get to experience the average of all of this weirdness. And thank you for watching.